Hello, infidels. This is Paul in my garage, and it's not even midnight. In fact, it's 7:30. So why am I dicking around in the garage at 7:30? Well, because it's coming up on Christmas, and I'm being highly unproductive and possibly entertaining you guys. So I have this lamb damper here, and this is for, let's see, this is for the back of a S197 Mustang, I believe. Twin tube damper, double adjustable. There's a compression adjuster there on the bottom, and a rebound adjuster here on the top, which you probably can bear. Yeah, you should see that now that it's zoomed in. And it's here for me to characterize. I just want to learn a little bit about it. Every damper is different, and there's always something to be learned. So as I was running it live, I saw some interesting things going on with the damping changing over time. So I quickly shut it down, put a fan on it to cool it down, and I thought I would start it again, run it, and put it on video and see what gives. So here goes. I'm going to run this at 30 inches per second, which is a pretty high velocity, but it's certainly attainable in operation. So we're watching this using the live screen, and so it's once I start it, it's going to plot the trace in real time, so you'll be able to see first cycle, second cycle, third cycle, and that's where the interesting things are happening here. So let me get this started. So there we go, cooking along, nothing new, but what's interesting to me is watching this trace change over time. I'm going to clear it. Watch what happens with each cycle. I can't tell you what's causing it. I haven't taken the damper apart. Even if I did, I still might not know. But notice we can monitor the temperature. It started at 72 degrees F. It's up to 80 now, and things are changing quite a bit. I'm gonna let this run for a while. We can all watch and scratch our heads, wonder what the fuck's going on. By the way, we can zoom in here on the scale. So here on the x-axis we have velocity. Of course, it's 0 at the far left. Goes up to, well, 30 inches per second, which is the maximum speed of the sine wave that's being fed in. And the force goes up to 500, down to minus 250 for the rebound side, just to give you an idea of what we're looking at here. And it appears that the compression damping has changed by about 100 pounds, which is considerable in terms of percent of total damping. And this bit of weirdness here in the middle from a delay in one of the valves is certainly interesting to watch. Again, I have no explanation for that. Seems to have stabilized up here. But I really don't know what the fuck is happening here. Although, I believe it's stabilized here as well. We're up to 132 degrees Fahrenheit, which is not an abnormal temperature at all for a damper on a street car, although you certainly wouldn't see that on the drag strip, so I'm going to stop it. All right, so there we have it. That was, well, let me see, this video's, well, I can't tell how many minutes long the video is, sorry. Maybe I will edit it later and take an estimate of the number of cycles that were there. In fact, I will do that. Before I post this video, I'll count the number of cycles and include it here in an edited version of this video, so you have some idea what was going on. And that's pretty messy, having a damper change that much over time. Now, what I see up there isn't, well, I'll say it isn't horrible compared to what I've seen with others. It's a little more stable down here. Again, I really can't explain any of that. It may make sense as I dig a little bit deeper. But there's one more point that I'd like to make before I go, and that is that I started by telling you this was a Lamb damper, and the point of this video is not to slam that company because there's no such thing as a perfect damper. The point of the shock dyno, particularly this one, is to show you everything that the damper is doing, both good and bad. And I don't care how much money you spend on dampers, I can put them on this dyno and show you things that they do wrong, or I should say at least less than perfect. So this is not a slam. This is simply a little bit of weirdness going on with this damper. And by the way, this isn't the first time that I've seen this. Many other dampers exhibit similar characteristics. So that's it. I'm not going to go into a lot of detail here about what's causing any of this because as I just admitted, I don't even know, haven't had it apart yet, but I thought you might find it interesting. And if you do find this interesting, meaning you know, watching what the hell a damper does, there are videos from CTW, the company that put this dyno together for me. They're here on the same YouTube page, and you can poke around there and probably learn a whole lot more than you might learn from these silly videos. So with the exception of one more thing, that's it. And the one more thing is fuck Shane. All right, everybody, have a good night. But wait, there's more. Didn't I say we were going to talk about Reynolds number? Actually, I didn't say that. I implied it by putting it in the title of the video. I meant to say that. So we're going to talk about Reynolds number because it's exciting stuff, right? No, it's not fucking exciting at all. Let me explain what it is. The Reynolds number is a number that quantifies the turbulence of flow of fluid. It doesn't matter whether it's a gas or a liquid. It describes the turbulence of that flow under whatever conditions it's describing. And so mathematically it's derived as or described as the ratio of inertia forces to shear forces within that fluid. So it sounds complicated. Like a lot of things, it's not. It's simple. I'm going to explain it, simplify it, and then I'm going to tell you why that relates to the previous portion of the video. And hopefully when I get all done, you'll get it and you'll be smarter, or at least you'll think you're smarter. That's almost more important. And most important, of course, is to sound smarter on Facebook. So anyway, let me stop fucking around and get to the point. So if we have a Venturi, a nice smooth flow path here, and we try to pump a high viscosity liquid through there, or fluid, right? Let's say honey or something like that. Differential fluid, it hardly matters. And we put some tracers in there so we can follow the path, the flow path. What we're going to see is what looks like basically numerous layers of this fluid flowing through here in nice clear streams, right? Being streamlined, that's where it comes from. I imagine it does. I don't know for sure. And so there is a velocity difference between all of these. The particles that are up against the wall are not moving at all. They have a velocity of 0, right? And the particles flowing through the center have the highest velocity. And so these layers of this fluid are flowing across one another, against one another, and there's a shearing force required to do that because it all just kind of wants to stick together and not be disturbed. And so that's described as the shearing force that is required to get that liquid to flow and maintain or to develop that flow path or that flow pattern where there's a difference in velocity. God, I hope I got that right. That sounded really fucking complicated. All right, so on the other hand, let's say that we have a flat plate orifice. And a flat plate orifice would be, you know, taking a piece of sheet metal, putting it in the drill press, drilling a hole through it. The flow through that is highly turbulent. I don't have to explain that. Everybody gets that. And, you know, if we could make the same drawing here, we may see some things here that make sense on the way in, but by the time it gets in there, man, there's just all kinds of shit going on if we could trace the path of that fluid. And so we have very little shearing force because we don't have these layers of fluid that we're trying to separate from one another because they're flowing at a different velocity. What we have is particles that are being accelerated this direction and that direction, velocities changing from one moment to the next, direction is changing, and just so you understand, even if velocity remains constant, but the direction is changing, that's also an acceleration. An example of that is driving down the road at 30 miles an hour, turning a car around a corner, there's an acceleration there, which is what throws you to the other side of the car. Hopefully you don't fall out. Anyway, that's an acceleration. There's an inertial force involved with that. And so what we have with this type of flow is a very high inertia force, very low shearing force. What we have here is very high shearing force, very low inertia force, all right? And so the Reynolds number, of course, as I stated, is a ratio of the two. Hopefully you get that. If you don't, it's not a big deal. Like everything else, just fucking Google it. I mean, everything is out there. The hard part sometimes is finding a simple explanation, but it's out there if you want to know. And if that's sufficient for you, which it probably is for most, race car guys, good, then we'll go with that. So now let's get to why this matters, right? So it's more than just a stupid fucking science project. Inside of the damper, we have fluid flowing, and at any point in that damper, we have a specific Reynolds number, which also changes with shaft velocity, okay? And so when the shaft velocity is high, and let's say we have, I'm gonna make another beautiful drawing here. We have our passages here through the piston, right, with our shim on top, and that shim is flexed up a little bit to allow the fluid to flow through here. It has to pass the sharp edge. Very, very turbulent flow. On the other hand, we often have an adjuster in the damper. One of two types are common. One adjusts preload on a valve or on a shim stack. The other adjusts flow through an orifice, and that might be implemented as, an orifice with a needle with a tapered seat. And when you screw it in, it changes the effective area here. And sometimes this is even rounded off like this to smooth the flow, which is really fucking stupid, by the way, and I'll explain more later. But because of the shape of this needle and the fact that at very low shaft velocities, the fluid flow is very low, this tends to be and can be a flow that has a very low Reynolds number. So now here's why all of this matters. When fluid gets hot, its viscosity changes, right? It gets hot, it thins out, okay? And so with this type of flow, flow with a high Reynolds number, a high turbulent flow path, we find that, as we know from the definition, that most of the forces involved are inertial, very little shearing force, and so the viscosity of the liquid doesn't matter much, right? Because as the viscosity lessens, the shearing force lessens, but in this case, that's really not much of a deal. It's mostly based on inertia force, and so the density of the fluid is what's important with this type of flow to determine the flow. Meaning, if you change the density, the flow changes a great deal. If you change the viscosity, it changes very little, okay? Now, on the other hand, when we have flow through the needle and seat at low shaft velocity, we have laminar flow, or, probably not strictly laminar like the definition that you see there, or drawn with nice, pretty straight lines, but we have flow with a very low Reynolds number. It's very dependent on viscosity, because as the viscosity changes, the shearing forces change, right? Fluid gets thin, shearing forces decrease. And so we find that, for instance, if you take a damper and you just change fluid from a thicker fluid to a thinner fluid, quite often when it's running on the bleed, which it is at low velocity before the shim stack opens, it's very sensitive to oil viscosity, which means it's going to be very sensitive to temperature, because no matter how much we try, even with the best oils, the viscosity does still change with temperature, some less than others. By the time we get onto the shim stack, it's highly turbulent. The effective viscosity is less. Now, I have seen a couple of piston designs, and one that even somebody modified intentionally to eliminate that sharp edge there at the port window, to reduce turbulence. I don't know what the fuck they thought they were doing. They were probably doing something related to high flow, because that's a really cool thing to say. To sell dampers, by the way, it has a high flow piston, as if they have any fucking idea what they're talking about. So somebody rounded those over, took the time to set it up on a rotary table, get a nice radius cutter in there and everything, and basically just fucked the damper up, and basically made it very, very much temperature sensitive at any shaft velocity. So There are some manufacturers, just a few, namely I would say Multimatic with their spool valves, the DSSV valves, where they've gone to great lengths to make the flow as turbulent as possible for exactly this reason. And what we find with dampers like that is that they're not very sensitive to temperature. And so this damper, this Lamb damper that's on the dyno, appears to be fairly sensitive to temperature, but as I said, it could be something else. I haven't been inside. However, you're going to find that because of the Reynolds number, which is largely determined by the design of the valve when the damper is designed, some dampers are very sensitive to temperature, some are not. Again, you can help that along by using good fluid. You can only go so far. If someone's designed a valve to have nice streamlined flow everywhere, or they put a nice radius on there and just went to all kinds of trouble to make the thing flow as smooth as possible and basically fucked it up, you're going to find that thing's very temperature sensitive. So I hope I explained that clearly enough, and if I didn't, I don't know what to say except, tough shit, it was free, or Google it, you'll figure it out. It's all on the internet. So, and if you do have a question, send it to me on Facebook. That's the easiest way to get a hold of me. If I respond, I'll do what I can to answer it. And then the last thing is that you probably noticed the little care package here, the micro penis cure tube. And the reason that's there is that well, we just finished PRI. That's a big event for all of us. We're all tired out. We get back and Christmas is coming up. And at some point, normally before Christmas, before I shouldn't say me, I get kind of lazy, right? So I got this list of shit that I want to get done. And one of those was to get this sent to my friend Shane Tecklenburg so that he could have it by Christmas, so that he could have a good Christmas, or, his wife could have a good Christmas. Anyway, so I was just procrastinating and I got lazy. And I didn't do it like I should have. I'm sorry, Heidi. I was just being lazy. I don't have a good excuse. Here I am fucking around doing videos instead of taking care of my buddy Shane, right? But I'll get it sent out next week. Hopefully you have it for New Year's. Start the year off with a bang. That's it. Everybody, have a good night.